P and Q are points on the diagonal BD of the parallelogram ABCD such that the length of BP is equal to the length of DQ. So our parallelogram ABCD can be seen here, A, B, C, D. Remember, a parallelogram is a four-sided shape, a quadrilateral, with two sets of parallel sides. So P and Q are points on the diagonal BD. So this is the diagonal BD, and P is one point on the diagonal BD, and Q is another point on the diagonal BD. And the distance from B to P is equal to the distance from D to Q. So that's why we have these little lines indicating equal length. Part 1. Show that the triangles ABP, so ABP, and CDQ, so CDQ, are congruent, and deduce that the distance from A to P is equal to the distance from C to Q. So congruent triangles are identical, so they have the exact same angles and the exact same lengths. Whereas similar triangles are basically just similar to each other. They have the same angles but different side lengths, but their side lengths are in the same ratio. So it's important to know the difference between congruent triangles and similar triangles. So we need to prove that the triangles ABP and CDQ are completely identical. Same angles, same lengths. So consider the triangles ABP. So ABP. So what I've done is drawn in an extra line to join up A and P. And CDQ. So CDQ. So again, I've drawn in an extra line to join up C and Q. Given the distance from B to P is equal to the distance from D to Q. So that was given in the question. So I've drawn in one little line in blue and another little line in blue to show equal length. So I've underlined each of these in blue and I've highlighted them in blue over here as well. So this line is equal to this line, or this length is equal to this length. So that was given to us in the question. So what else do we know? Well, the angle ABP, so ABP, so this angle here I've drawn in red, is equal to the angle CDQ, so CDQ, so I've drawn that in red, because they are alternate angles. So if we were to extend the parallel line at the side and the parallel line at the other side, then the diagonal would be a transversal cutting through the parallel lines and would be easier to see the alternate angles. So you can actually draw in some extra lines if you want to help you out, that's no problem. Just make sure that everything else can still be clearly seen. Okay, so by opposite sides of a parallelogram, so by this theorem, the distance from A to B is equal to the distance from D to C. And I have drawn them in green with two little lines representing equal distance. So we know that opposite sides of a parallelogram are equal. So likewise, the distance from A to D is equal to the distance from B to C, but we don't need that right now. Thus, the triangles ABP, ABP, and CDQ, CDQ, are congruent. And they are congruent by SAS. Side included angle side. So we started off with the blue lengths, and then we found the interior angle or the inside angle, and then we also found that the green lengths were equal. So we have a side, an included angle, and a side. A side, an included angle, and a side. So therefore, all the other sides and all the other lengths in the triangles must also be equal. So hence, the distance from A to P is equal to the distance from C to Q, and that's what we were asked to prove. We were asked to show that the triangles ABP and CDQ are congruent, which we did, and deduce that the distance from A to P is equal to the distance from C to Q. So AP is equal to CQ. Remember that the other forms of congruency are ASA, angle, included side angle, SSS, side side side, and RHS, right angle, hypotenuse, and another side. Part 2. Prove that APCQ is a parallelogram. So now we're going to consider the triangles BPC. So BPC. So we get that triangle by joining together the P and the C. And the triangles AQD. So AQD. So again, we get that triangle by joining together the A and the Q. The distance from B to P is equal to the distance from D to Q. So the distance from B to P, drawn in red, is equal to the distance from D to Q, also drawn in red. And this was given to us in the question. The angle PBC, so PBC, so this angle in here, drawn in blue, is equal to the angle QDA. So QDA, so this angle drawn in here in blue. And this is because alternate angles theorem. So we can see we have our BC parallel line and our AD parallel line. And if we were to extend them and draw in a transversal, we would more clearly see the alternate angles. So the angle BBC is alternate to the angle QDA, drawn in blue, so they are equal. Now we're going to look at the length BC. So BC, and the length AD. So they are also equal because they are the opposite sides of a parallelogram. So BC is equal to AD. So they're drawn in green with two little lines. Thus, the triangles BPC, so BPC, and AQD are congruent by SAS, so side included angle side. So the red lengths BP and DQ, they are equal. The blue angles BPC and QDA, they are equal. And the green lengths BC and AD, so BC and AD, so they are equal. So we end up with side included angle side. So side included angle side, and side included angle side. So we've proven that the two triangles are congruent by SAS. Hence, the distance from PC must be equal to the distance from AQ. So PC must be equal to AQ. So they're done in purple. And that is because all the angles and all the sides in both triangles are equal to each other. Well, all the corresponding angles and the corresponding sides. So we've now proven that PC is equal to AQ. We know that BP is equal to QD. We know that AD is equal to BC. And we know that the angle PBC is equal to the angle ADQ. Now consider the quadrilateral APCQ. So APCQ. So it's this quadrilateral that's on the inside. AP is equal to CQ. So AP is equal to CQ. We already proved that in part 1. And PC is equal to AQ. PC is equal to AQ. We proved that here. So as these are equal, APCQ is a parallelogram by the converse of the opposite sides and angles in a parallelogram theorem. Because basically, since we have proven that all the angles inside of the parallelogram are congruent, so this triangle ABP is congruent to this triangle CQD, this triangle ADQ is congruent to this triangle PBC, and this triangle APQ is congruent to this triangle QCP. So they're all congruent, which means this diagonal here forms a mirror line. We've got the exact same shapes on the top of the diagonal as we have on the bottom. So therefore, this length must be equal to this length, and all the angles must also be equal. So therefore, our shape is a parallelogram.